Okay, next, now we are at question 15. Which of the compounds are insoluble in water, and which is the reason, and which are the compounds which are soluble in water, and give the reason. Okay, so for the solubility wise, I will just put it at the other side so that you can take down, because I think there could be some things that you need to know. So out of the compounds, we have water as the solvent, right? So, and we have butane. Okay, if you do not know what is butane, it's C4H10, which means that it's just hydrocarbon. Chloroethane, we have C2H5Cl. So it looks like this. Okay, that's chloroethane. And we have propanone. Propanone looks like this. Let me draw out the structure for you. And the last, we have propan-1-ol, which looks like this. Okay, so in order for you to understand, let's use a symbol to represent them so it saves me from drawing. Let's call all these things the solute. And we just call it S. Okay, so S represents one molecule. So S another molecule and so on. Okay, so let's look at S first. So remember about solubility, it's about mixing. So this is my water. Remember the demonstration in class, right? So this is my water. So if they do not mix, they will stay water, one chunk, solute, one chunk, right? So we need to see what is in water first. In water, there's already hydrogen bond. So maybe some form of hydrogen bond, which is very strong. And in the solute, we need to look at each solute and see what is the intermolecular force. So for example, if it's the butane, which is non-polar, the intermolecular force is LDF between the S and the S. For C2H5Cl, it will be dipole between the solute. For propanone, it is polar, it's polar, but no hydrogen bond because I don't see H, I only see O. So it's dipole between the S. And the last one, where I see OH, right? So it's hydrogen bond between the S. So there are some forces already between the S solute, but we have to be aware they exist. So in order for this and this to mix, we actually want to achieve this state, this idea. Solubility means I want to achieve something like this, where my S and my H water are well dispersed. And I have some bonds between them or something like that that keeps them in place, right? But the thing is, so what we are seeing here is that we need to form some new interactions or form some new attractions, right? Or form some new bonds. And here, they are the old ones. There's existing ones that we need to break or overcome, right? We need to overcome the existing ones. And we need to overcome these existing ones, right? So therefore, the energy that is given out from the new bonds formation should be able to overcome the ones that you need to break all these up and break all these up. Then you can mix, right? So the thing is, then we have to look at the comparison. So this itself is hydrogen bond, which is very strong. Okay, and this varies between the solute because I have 4 different examples of solute, right? And overall, what is formed is the key, before it's formed, must overcome the hydrogen bond and the bond that is already existing, intermolecular force already existing in the solute. So the new interactions must overcome intermolecular force, hydrogen bond, plus what is present in the solute already, right? So the only thing is like, say, you cannot like you must compare it the same with the same, right? You can't be like comparing a stone with a feather. Like it's not able to overcome the feather, right? The stone and the feather is quite different. So in the same way, at least you need something that can form a hydrogen bond to give out enough energy to overcome the hydrogen bond, at least in the water, that as well as other intermolecular force in the solute. So if I'm not able to form hydrogen bond with the water, then it's unlikely it will be able to dissolve. Okay? So usually we can see in this point of view. But in actual exam, you don't need to write such long stories. So in actual exam, you just need to just write down whether this thing is able to form hydrogen bond with water and therefore is soluble or is not soluble. Right? So if we go back to each one, then we can see, okay, we have butane. Butane is non-polar, right? Since it's non-polar, is most probably only able to form London dispersion force with water. Chloroethane is polar, but it's not able for hydrogen bond. It will only and most form van der Waals with water. Van der Waals is dipole-dipole plus LDF. Propanol is polar, but it doesn't form hydrogen bond that well. So it is only maybe able to form van der Waals with water, which is dipole-dipole plus LDF. So propanol is a little bit better. So propanol is able to form hydrogen bond with water and because it itself has O and H. So if we classify what is unlikely to be soluble in water, most probably it will be the butane, it will be the chloroethane, and it will be the propanol. And what is soluble in water? It will be propan 1-ol. Okay, so then the reasons will be that we have to talk about propan 1-ol is able to form hydrogen bond with water and therefore is able to overcome the existing solvent and solute interactions. Whereas for butane, chloroethane, and propanol, what we can say is that it's only able to form van der Waals or London dispersion forces with water, and hence is not able, the energy given out is not able to overcome the existing interactions in the solute and the solvent. Okay, I think that would be enough as the answer, but of course I will post you the model answer, which may elaborate everything in greater detail, but that's the idea behind it. Okay, so that's all for question 15.